Well, hopefully everybody got PA5 turned in. And I will get those graded up this morning, or this weekend, not this morning. Final prep week. Yeah, so for this class, we're pretty much past, the bulk of it, except for the exam. We've got more things to talk about. We'll talk about interfaces and generics today, and maybe look at some source code, and talk a little more about some data structures next week, and look at Android development, and sort of pick up some neighboring topics along the way. But we've pretty much gone through the bulk of the course, the core material certainly. And you're done with assignments at this point, other than the final exam, and turning in your SLP report, and then showing up for presentation Monday. So the end is well within sight, and that's pretty exciting. All right, so questions. Lingering issues with PA5, or things you want to go over? Passing mouse clicks. Were you able to pass names? If you can pass names, then you should be able to pass mouse clicks. The main issue is the timing of it. No, you don't need to handle bad IP exceptions. You can assume that you're connecting to the correct server. Players are well behaved for PA5, so don't have to do a whole lot of error checking. Just don't allow illegal moves. But other than that, the players are competent and honest. Well, I can dig into a little bit of code. I don't want to pull out a lot of code yet. But so here's some sample code. So a lot of this looks like what you did in PA4, for example. So I had my mouse listener in my main panel, right? And this is stuff created by Window Builder. So first thing I wanted to do was make sure that it's your turn, right? If you click the mouse and it's not your turn to make a move, don't do anything except yell at the user and just ignore it. Don't send anything, don't change turns, stuff like that. So right up front, if the current turn is not the same as who I am, right, I just print a message and return, right? So the click is basically a non-event. If the game's not running, I just go ahead and return, so it's not an event. Otherwise, right, here's where I pick up the XY coordinates, and then I call a method that basically responds to that click. So the click method is figure out what row and column you're in on the board, see which edge you're closest to, see if it's already set, etc., etc. So that's all the stuff that was in PA4. And then one extra line, which is go ahead and send that XY pair to the other player. And that's using this method inside the network object. Did I say nope? Oh yeah. And click. So I don't know what game is. It's a main panel. right? So click. This is code from PA4 basically, right? Some text messages. Make sure that you're running. Figure out the row and column by doing that coordinate arithmetic. Make sure that you're inside the board area. Um, find the box from your board array. Find your distance to the top, bottom, left, and right, and see which one is smaller. And so if left is smaller, then we're trying to click on the left line. And if the left side is already taken, then print a message. Otherwise, set it to true and set the box to the left. All of that stuff that we did in the previous one. And then when that's done, right, check to see if a new box has been filled in, set a flag, update the score. If a new box didn't get filled in, change the turn, show whose turn it is, see if anybody won, and then finally call repaint to make all of that visible. So that's all, stuff from before. And the threading, the network stuff, I think most people have already figured out. So it's a class that extends thread so that we can run it as a separate thread by calling the start method. And the constructor, right? I kind of had my classes all over the place, so I passed in the main JPanel, the parent JFrame class, and a flag to say if this is the client or the server, and I save those. And the starting of the thread is create the server socket if you're the server, accept a connection, make a print writer or scanner, send a name, get the other player's name. If you're the client, construct a socket to connect to the requested machine on that port, make your print writer, make your scanner, send your name, get the other player's name. And then whichever identity you have down here, then we go into our infinite loop that basically reads the next line from the socket. I mentioned in the assignment to take a look at the split method for a string. That's a useful way to break things up. So if you have a string like something and a space, something else and a space, something else, and you say dot split, quote space, it will give you an array where each element of the array contains those things that were separated by spaces. So my protocol was an N followed by a name, or an X followed by a coordinate, or a Y followed by a coordinate, or a Q. And so if I do a split, I get this tag in element 0, and I can parse based on that. So if element 0 is Q, it's a quit. If it's X, then I parse the coordinate and save that as X. If it's a Y, I parse the coordinate and save it as Y. And my protocol was, after you get the Y, then you've got an XY pair. So I go ahead and call click. And then the name, we just send an N followed by the name. And the send click just prints out the X and Y coordinate pair. Realized I hard-coded localhost into my connection for the client. I had the box to enter an IP, but hard-coded value. Tried to figure out why I got connection refused. There you go. Cool. Good catch. Did you have to declare your net.object as a public static net dot? I don't think I used any statics. So net thread gets declared in the main panel. Interesting. So I declare it inside my J panel, right? The my panel. And then I construct it here, or I save it here. I think I actually constructed in the JFrame though. Right, so this is the actual thread. And it gets constructed right here in the start button or connect button listener. So when you hit the start or connect button, go ahead and construct that thread, but I pass it a flag saying whether it's the server or the client. And then go ahead and start it, which begins its run method. And then I also save that thread ID, right, that object inside the JPanel. The only time it might have to be static is if you were to put it into the main method. If I tried to declare it inside here, then you might need to make it a static. But if you declare it, you know, in this class but outside of main, that's legit. Because what main is doing is it's creating an instance of this object, right? Net dot. First thing main does is make a thing called frame, which is a new net dot. And then inside frame, we can, you know, frame is an instance of that class, and so we can treat things in there non-statically. Interesting. Eclipse should not be initializing your net dot object. Yeah, it constructs a net dot, but the net dot should be, you know, if it's called frame, frame should be local to this. But within frame itself, right, that's an instance. What is mainframe? Do I have a mainframe? Oh, I see. Yeah, that's just a name I used, so I just did mainframe equals this. So, and I think I did that so that I could pass that to other other objects, so that I could do things like get a hold of the text fields and so on and so forth. So I passed it mainly to my my thread, so that it could come back and fill in the player names, I think was the main thing. So yeah, that's the instance of net dot. Yeah, so statics we rarely need, and you can actually live without them. And I know this because when I first tried to learn Java, I didn't bother trying to learn statics, and I didn't use them, but I had to write some really goofy code as a result. So here's a real life example. Right, so I was building a Java package to work with a number of things, one of which was called a cell. And a cell had, you know, a truth table, which was an array of Booleans, and it had, you know, some other stuff. And I also wanted to be able to do something to these truth tables. And so, you know, I'd have some methods for, like, you know, reset truth table, which would, you know, clear out all my Booleans in here and make them false, things like that. But it turned out there were other things I wanted to do with a cell, such as, I don't know, take an equation and convert an equation from reverse Polish notation to algebraic. So I wanted to take something like, you know, A, B, and change it into A and B. It's one of my last fruit flies there. And this was a function that takes a string and returns a string. Okay? The specifics of what it does isn't important, but this operation was related to the kinds of things I was storing in this class called a cell. And so sometimes I'd be writing code and I wanted to use this function called convert, right? And here's what I had to do. I had to do something like, cell temp equals new cell, and then I could say temp dot convert old string, and I could say new string equals temp dot convert. And every time I wanted to use this function, first I had to construct a cell so that I could say, name of that object dot convert. And convert doesn't do anything with a cell. It takes a string, it gives you back a new string. But it made sense to make it part of this cell class. And it's kind of like square root, right? Square root takes a number, gives you back the square root. In the integer class, there's a method for parsing a string and returning an integer. And they're useful methods, and they belong in that class, but they don't actually act on an object from that class. And so every time I wanted to call this method, I had to first construct an object just so I could say object name dot convert. So if instead I had said, inside the cell class static, string convert string arg, then instead of doing this, what I could do is something like this, new string, and instead of creating an object of type cell and using that, I could just use the name of the class, cell dot convert old string. So by making this method static, I'm saying I'm not going to use an instance of a cell to run this. I'm just going to use the name of the class itself. And so when this is running, there is no cell object that it's running inside of. When we have a rectangle and we say area, that instance of the area method is being run inside, a rectangle. There's a height and there's a width. But in this case, I'm saying I don't have an instance of a cell. I'm just using this method that happens to be part of the cell class. And the example I go back to a lot of times is square root, right? If we didn't have statics, and I wanted to find the square root of a number, what would I have to do? I'd say something like math, temp equals new math, and then y equals temp dot square root of x. That works, but it's goofy, right? Why did I create an instance of this object? I did it just so I could call the square root method. And then I'm done. I just throw this object away. I let the garbage collector pick it up, right? So instead, square root is defined to be static, which means I can say y equals name of the class dot square root x. But unless you have a method or a field that you want to use or you want to access independent of an instance, right? Unless that's the situation, don't use a static. Object-oriented design means, we have classes which are blueprints, we have objects which are constructed from the blueprints, and then inside those objects we can access fields, we can access methods, and so on. That's the object-oriented mindset. This is kind of an aberration of some sort, right? It's saying that I want to use a method or a field without having a particular instance of the math class, right? And same thing with math.py. If I didn't have a static, I'd say, p equals temp.py. Well, I don't have to do that. I can just say p equals math.py. But that's not usually something we're going to encounter in the projects we've been working on. The main case that this pops up in first is probably constants. If you have a constant that's going to be defined, forever and ever and ever and has nothing to do with a particular instance, then you could make that a static, you know, integer or string or something like that, and you could access it with the name of the class dot constant. Let's see. So the frame is basically the same thing as mainframe, basically. Yes, that's correct. I think so, yep. When I initially built the frame through the design menu in Eclipse, that was called an instance of netdot, yeah. Originally my class was dot, then I renamed it for PA5. Okay, that's fair. I think your problem was dealing with RPN. RPN is pretty fun though. When would we need to make an object static versus a method static? So like pi is declared to be a static. So objects aren't static, right? But methods and fields can be static. Objects themselves aren't something that can be modified with the notion of static or not static. But a field like pi, right? Pi is a double inside the math class, but it's set up to be static. Oops. So all of these methods that belong in the math class, because they're mathy, right? These are statics. And there's two constants that are also static, pi and e. How many digits does pi use? Don't know. Good thing to try to find out, though. So, I mean, you could print pi, and then you could subtract the double precision number that you saw from pi, and multiply by 1,000,000 and see if you get 0 or not. It's a fun thing to dig into. Totally random tangent question. Has anyone ever tried programming Conway's Game of Life? I saw a video of it recently and thought it looked super cool. That's a really cool project to tackle. And you've totally got enough Java and Swing and stuff to be able to code that up in Java if you want. And the underlying engine, so Game of Life is a cellular automata, which I'm not going to go into right now, but I think someone posted a video for that, or maybe for Rick Roll. You know, it's a pretty simple engine for updating each cell, and you know, make pair nested for loops, update the cells, and use your paint method to display, you know, cells in two colors based on values stored in an array. Totally something that everybody here can do, and pretty fun once you get it working to play around with different programs and see what kinds of things you get.
Grammarly helps you work more efficiently.
I'll take a shot here.
Accomplishing your work goals easier.
All right. There we go. Yeah, I can't handle Cronus Quartet though. But yeah, so this would be a cool project to play with over the summer or something, if you're looking for something to do. And it's a good exercise for, you know, doing all the stuff we've been doing in Java, including the GUI aspect. And you get into some really weird stuff. John von Neumann did a lot of exploration on this. He came up with a self-replicating system as a cellular automata and so on. Or the Game of Life, playing the Game of Life. Excellent. All right, cool. Anything else? So let's just talk a little bit about interfaces, and this is related to this idea of implements runnable that we worked with Wednesday. So remember in 222 when we were talking about data structures, and I kept talking about the idea of abstract data types. And the notion of an abstract data type was if we have something like a hash, right? We implement our hash by making an array, and we have a hash function. And you take a string and you add the ASCII codes and you multiply them by the position in the string, and you reduce modulo 79. And that gives you a number, and you go into an array. And at the index given by the hash function, you find a sentinel node for a linked list. And if you move down that linked list, you'll find the keys that were stored that hash to that index, right? And none of that is interesting or useful to somebody who wants to use your hash package, right? Those are all implementation details, but the person who's writing a program that wants to store words and retrieve words to make a word index program, they don't really care about any of that. They don't care about what your hash function was, the fact that you used an array, the fact that your array contains linked lists, the fact that you have sentinel nodes, the linked list is implemented using this kind of structure. None of that's relevant, right? So what does the person who's using your package care about? They want to be able to initialize your hash map. They want to be able to fetch based on a string. They want to be able to put, say, a string and a second string. And the fetch should return a string to them. I don't know, that's a nominal set of functions. You want to be able to, like, iterate through and see how many things are in there and so on. But suppose this is all you care about, right? This is the user's interface to your hash code. And whether you're storing things using this hash function or that hash function doesn't affect, the fact that when I want to get a string, I'm going to say fetch, and I'm going to pass the string. I want to get the string back. Whether you're storing this, using some kind of probing to deal with collisions, or you're making a linked list of entries, doesn't affect the fact when I want to get a string, I just say fetch, give it a string, I get a string back. When I want to store something, I say put, I specify the key and the value pair, and it stores it in your hash. So this is the abstract data type view of your hash, and then underneath there's all the gory stuff going on, the code, the arrays, the hash functions, the modular arithmetic, right? But that's all hidden from the user. So this is the interface that the user has to your collection of methods, to your implementation of this structure. So in Java, we can specify an interface that basically says what kinds of methods somebody implementing this interface should create. And what should their signatures be? What arguments should they take? What types of arguments should they return? And we specify an interface, but we don't actually specify the code that makes up these methods. We're basically just creating a template, okay, which says, okay, you need to write an init method, takes no arguments, returns void, a fetch that takes a string, returns a string, and a put that takes two strings and returns void. And once we've defined this, somebody can say, okay, I'm going to make my own implementation of a hash. And they can say, my hash implements hash, and as long as they specify these three methods, they're good to go. Now they can specify additional methods, and absolutely they can do whatever they want inside these methods. So one person might, use a simple hash that makes linked lists. Another person might use a very complex hash that uses probing. Another person might, have this send a text message to a friend who writes down the string on a whiteboard, right, and texts back responses when you say fetch. They all implement the same interface, though. So interfaces are a way to let us do this. So let's play with this. All right, so let's make an interface called a shape. And we're always going to want, whoever decides to implement one of our shapes, we want them to write a method for finding the area and a method for finding the perimeter. Okay, we're going to require that. And so we could do something like this. We can say class shape, sorry, interface shape. And we kind of do like prototypes for functions here, right? So I'm going to say public area, which takes no arguments. Public perimeter, which takes no arguments. And let's require a method for initializing the shape, for making a shape of some magic initial dimensions. So these two things are, let's just suppose we're doing integers. And then let's have an initialize method that takes some size and gives you some default shape. So for an ellipse, it would be a circle. For a rectangle, it would be a square. For a triangle, it would be an equilateral triangle, or whatever. All right, there's our interface. All right, so what does this do for us? Right, we can compile it, and it doesn't do much. But let's suppose we want to make a rectangle. Well, let's do a triangle. So I'm going to say class triangle implements shapes. Wow. Class triangle implements shape. So I'm saying I want to use this interface that's been defined by someone, and that means I need to supply, you know, at least these methods that were described in the interface. So I don't know, I might have, you know, integer height and width, which are terrible names. So public int area. So we'll return height times width over 2. And it doesn't matter what these methods do. There's nothing in the interface that says this has to actually return the perimeter of the shape, right? The interface is just saying what kinds of things do we need to supply. And the idea is somebody who's writing a main program to interface with a triangle, if they think the triangle is a shape, if they want the area, they're going to call a method called area, A-R-E-A, lowercase. They won't pass anything. They'll expect to get back an integer. So it's a way to sort of put some structure on how somebody would create a class that conforms to this interface. And it's different from extending a class, right? Extending a class means we have some base class that already has implementations of these methods, and we can inherit those and we can modify them if we want, override them, or we can add new things. In this case, there's no base code there. It's really just sort of a template. And if I try to compile this, it's going to complain that I forgot to do an init function. So I need a method called init that takes an integer and returns void. But as long as I have all of these things here, right, I can compile that. Alright, so I can construct a new triangle, I can call the init method for it, which should make it, a height of 4 and a width of 4, and then I can call its area method. Alright, and that's the height of a 4 by 4 triangle. Yeah, I tried to use tab to autocomplete, but I didn't have a main, so we're living with may instead. So that's basically what an interface is. And when you write swing code, and you right click on an object and say I want to add an event handler. If you look inside your code, you'll see event listener. Well, let me just show you some code. It should also freak you out that I've totally misspelled programming assignments, but I can't change it at this point. So for example, the start button, right, this was PA4 code, the start button said add action listener, new action listener, curly bracket. And an action listener is an interface. And this particular interface, you're required to implement one method, which is called action performed. And so we've been using this idea of interfaces since we started playing around with Swing and Window Builder, but it's mostly been written for us. All right, so that's just something to be aware of, and most object-oriented languages have something similar to this. Where are we? We got 11 minutes left. Let's talk about generics. So remember, a generic is when you want to make a linked list, for example. We saw this kind of syntax where we could construct a linked list or we could declare a linked list, but when we do either of those things, we need to specify inside angle brackets some kind of type, for example, string or rectangle or triangle or whatever. And the reason for this was that the code that makes up a linked list really doesn't change depending on whether the list is storing strings or integers or rectangles or hash maps or other linked lists. The code is exactly the same. If you were to write this by hand, the only thing that changes is, in some places you would say string data, and you'd have to change that to integer data or triangle data or linked list data. And so a generic is a way that we can specify a class with a placeholder. And this is kind of like, a variable that by putting something inside angle brackets, we can have a variable that takes on the value of what we put in here, string, for example. And we can use this to implement classes more generally. So let's make a stack class. So I want to make a class stack. And let's think about a stack of integers first. Okay, so we're going to have a root node, which I'm not going to do a sentinel node, so our root will be null by default. And then we're going to have a push, which takes, let's make it a stack of strings. So public void push string data. And so how do we do this? Node temp equals new node. Temp.data equals data. If the list is empty right now, if there's nothing in the root, we'll just set the root equal to the temporary node and return. I'll just do typo Friday. So the way I'm thinking of this is we're going to have a linked list. So this is a stack. And when I want to push, I'm just going to insert right in the beginning. And when I pop, I'm just going to pop from the first node. So stacks are nice. We don't have to traverse down our list. So we're just going to have a linked list. We add to the beginning. We remove the first node to push and pop. Stack is not empty, push in the front of the list. So we've got a temporary node, so we'll do the following. Temp next equals root. Root equals temp. And that's the end of our push routine. And push should just, pop should just remove the first element from the list and return that. So, this is an edge case. We're not going to worry about stack underflows, but if the root happens to be null, we'll just return null. Otherwise, we'll do the following. We'll take the current root, that's the thing we want to return, right? And then we'll remove it from the list. All right, so there's a really simple stack implementation, okay? And don't get bogged down on the nuances of how this works, but we've got a node. We can push by inserting in the beginning of the linked list. We can pop by removing the linked list. So here's the thing: is this works for a linked list of strings of your push? Yeah, I think that's the one I just fixed. Cool, thank you. So this is a linked list of strings, but really the only reason it's a linked list of strings is because I said the argument to push is a string, and I said the return value from pop is a string. And those are the only places that the word string appears. If I change this to integer, I've got a linked list, a stack of integers now. And if I changed it to triangle, I've got a stack of triangles. So we can make this generic. All right, and the way we do that is when we declare class stack, we put angle brackets and we put a placeholder in here, and typically you see T for type. So whoever is writing code that's using this generic class stack, they're going to put some type in angle brackets, the name of some class. That's what T is going to be. And so down here, when I say triangle, instead of saying triangle, I can just say T. And if someone says, you know, I want to stack angle bracket integer, this will say integer data, this will say integer pop. If they say stack angle bracket rectangle, this will say rectangle data, this will say rectangle pop. And so now we've taken this code and we've made it generic. You can construct your stack and declare your stack with any type that you want in here, and whatever type you specified, that will be used right here and right here. So this supports code reuse. And to finish the stack example, we need to be a little careful because guess what? Our node also depends on knowing what kind of thing we have here. So if I make my node.java, right, this is normally what a node looks like, but we don't know if this is supposed to be an int or a string or a triangle. So we can also make this generic. It doesn't have to be the same name, it's just a placeholder. T is just a variable. And then down here I'm going to say, you know, data is an object of type T. But my node, my next field is going to be a node, but what kind of node? It's a node of type T also. So we're getting some recursion inception here. And so back here, whenever I talk about a node, this has to be a node of type T. This has to be a node of type T. This has to be a node of type T. So let's try a main method. So we'll make a stack of integers and we'll call push and we'll call pop and print those out. I have no idea if this is going to compile or not. Temp root. If root is null, return null. Node t temp equals root. Root equals root next. Return temp. What didn't it like? Node t cannot be converted to t. Return temp dot data maybe. All right, so we're going to push a 2, a 3, and a 5 and then pop them off. And so we pop off in the reverse order, 5, 3, 2. Second time's a charm Friday, perfect. So if instead of doing this, I say stack string, have a hood weekend. Alright, so we pop off our strings in reverse order. So that's the basic setup, right? Yeah, I did this a few days ago to figure out the details. That's why it didn't take me an hour of trial and error. But it did when I set it up a few days ago. So, yeah, so that's the basic setup. So I'll push this over to the server under a generic directory, and it's just something to throw in your tool bag. So, all right, cool. We are out of time. Monday will be SLP presentations. Do not come into the class. Come into the Zoom room that's listed under the SLP presentation item on Canvas. So I'll see you there for presentations, and then Tuesday we'll talk about the URL class, and then we'll go on from there. All right, cool. Have a good one. Enjoy the day and the weekend. I'll see you next time.